Alright, so to start our unit on gases, we need to first talk about all three states of matter so we can really understand what makes a gas a gas. And to really understand what makes a gas, we need to understand the kinetic molecular theory. So the kinetic molecular theory is the way that we describe what it is that creates different states of matter. You've probably never really thought about it, but think about this. So we know the three states of matter: solid, liquid, and a gas. And we know that water, it's a very, very common substance all around us. We've seen all three states of matter for water: a solid chunk of ice, a glass of water, and then steam or water vapor that comes off a boiling pan of water. All three of those are the exact same molecule. There is absolutely no difference between ice, water, and steam except for one thing, and that is the kinetic motion of the molecules. All three of them are just H2O, so it's one oxygen attached to two hydrogens, and then oxygen's got the lone pairs on it. No matter what, solid, liquid, and gas, it looks like this. Does not change. They have different properties, they feel different. We can drink one of them, we can see two of them, but we can't see the third one. So here is the kinetic molecular theory in definition form. So by definition, the kinetic molecular theory, kinetic, that's a fancy word for motion, molecular, that is molecules, and theory, that means we've never actually seen this, we're just guessing this actually occurs based upon observations. So molecules are always in motion. Doesn't matter what state of matter they're in, molecules are always moving. Take your hand and put it on the chair that you're sitting on right now. Do you feel the molecules in that chair moving? You probably don't, but they actually are. It's just that the motions in a solid are so imperceptibly small that we cannot feel them. It's just a vague vibration back and forth. So in this little picture right here of the solid, those molecules are very, very slightly vibrating back and forth. They're moving. Molecules are always moving. That's the kinetic molecular theory. Then if you put your hand in a glass of water, you can kind of swish your hand through it. You can feel the individual molecules in there. In that case, in the case of a solid, those molecules are sliding around past each other. So we can say that in a solid, the molecules are vibrating. In a liquid, they're sliding around past each other. And then a gas. Oh, the gases. Those molecules are really moving around. In fact, they're moving everywhere. In the case of a gas, the molecules are bouncing all around. That's what causes pressure. That's what causes them to fill up the entire container that they're in. Gases are everywhere. But the fact is, molecules are always moving, even in the coldest solid, in the back of your freezer where it's absolutely frigid. All of the molecules in that block of chicken that's been sitting in your freezer for years are still moving, because there's always energy coming from somewhere. The molecules slow down as they get colder because motion is related to temperature. So as we go down this little chart right here, as we move from the left to the right, those molecules are moving faster and faster and faster. So here they're vibrating, here they're sliding, here they're bouncing. In each case, the temperature also increases, the relative temperature. So we know that ice is colder than water, which is colder than air. Gas or steam would be the hottest of all three states of matter. And it's all relative. I mean, if you fill your chair isn't at 0 degrees Celsius, and it's still a solid, so it's relative to the individual compound. But as you heat different things up, so as you take a block of ice and you heat it up, the molecules start moving faster and faster and faster, and eventually they turn into a liquid, and then they move faster and faster and faster, and then they turn into a gas. And that's where they stop. So what causes states of matter is the motion of the molecules, and what causes the motion is the temperature. This is why when we heat things up, they change from one state of the matter to the next, or when we cool them down, they change back into a liquid and then eventually into a solid. Speaking of temperature, this happy-looking fella is Lord Kelvin, and Lord Kelvin actually found us something really important about temperature. So the kinetic molecular theory does say that molecules are always in motion, but in theory, there has to be a point, if you take away all of the energy, that every single bit of motion will stop. Where a solid will actually freeze solid, where the molecules aren't even vibrating in that. And that's what Kelvin came up with. He figured out the temperature at which, in theory, all motion would cease. And he called that temperature absolute zero. Absolute zero is, in theory, the coldest temperature that is possible. It is the point where molecules literally stop moving. So it defies kinetic molecular theory. It's the point where all motion would stop. It's impossible to ever get there because there's always energy that's going to come from somewhere, from the sun, from the other matter that's touching it, even from the stars in the distance. There's going to be energy coming from something. Even in the vacuum of space where it's extremely cold, there's still going to be some energy, and so it's not even absolute zero up in space. So in terms of numbers that we know in degrees Celsius, absolute zero would be negative 273 degrees Celsius. So if we were able to get something down to negative 273 degrees Celsius, it would be at absolute zero. The molecules in whatever that substance would not be moving. They wouldn't even be vibrating with each other. We also put this in a scale that's called Kelvin, named after Lord Kelvin himself, and we call absolute zero 0 Kelvin. Okay, so instead of referring to negative 273 as absolute zero, 0 Kelvin is absolute zero. So it's a pretty easy conversion, and throughout the gases unit, you need to put everything always into Kelvin. And it's because Kelvin is a relative temperature. If we think of degrees Celsius, 50 degrees Celsius, if you warm it up to 100 degrees Celsius, 100 degrees Celsius is not twice as warm as 50 degrees Celsius. That may seem confusing, but it looks like it from the numbers because 100 is double of 50. But the amount of energy that's in a substance at 100 degrees is not double 50 degrees. Okay, so it's not a relative scale. It's not a good scale for that sense. But in Kelvin, it is. So 50 Kelvin would be half as warm as 100 Kelvin. Okay, that's why when we do calculations, where we look at correlations, direct and indirect correlations, we use Kelvin, not Celsius. A lot of the temperature readings that we're going to get are always going to be in Celsius. That's what most thermometers are in. You need to be ready to convert every single degrees Celsius into Kelvin. And it's a real simple conversion. All you do is you take the degrees Celsius, boom, and add 273 to it. Yep, it's that easy. So for example, room temperature is about 30 degrees Celsius. If we wanted to put that into Kelvin, we would just add 273 to it. And that would mean that the room is 303 Kelvin. Kelvin is not a degrees, it's an absolute temperature, so it's not 303 degrees Kelvin, it's just 303 Kelvin. If we're somewhere really cold where it's negative 10 degrees Celsius, we would still add 273 to that, and in Kelvin, that would be 263 Kelvin. So there you go. There's the kinetic molecular theory and a little bit about temperature. So here's a hint. Next time you're sitting around whining about how it's absolutely freezing in here, that's not true. Nothing's absolutely freezing. Not even space is absolutely freezing. It's impossible.